Well, hi there, sports fans, and welcome to another exciting edition of Physics 12. Today we're looking at lesson 3.6, which is on one-dimensional collisions, also known as, or AKA, conservation of momentum. And so, obviously by saying that, when you have these types of collisions in one dimension, then you have conservation of momentum in these collisions. And we will be exploring exactly what we mean by that. So conservation of momentum, what that means is that if you have two objects that are both have a velocity, so anything that has a mass and a velocity has momentum. So these two objects both have mass and velocity, so they have a momentum attached to each of them. Notice one is going in the opposite direction to the other one. So this one, it's if we define the positive direction as that direction there, then this one will be positive, but then this one will be negative. So always watch out for that when you're dealing with momentum, because momentum is a vector like velocity. It's based on velocity times the mass, and so you always have to make sure you got your plus and minuses sorted out that way. So if these two objects, they collide, if you look at the total momentum of the system before the collision, so you calculate the momentum of this, and then you add the negative momentum of this one. After the collision, then the total momentum of the two objects again will be the same as the initial. So after the collision, momentum, as they say, is conserved, and so if you calculate the momentum of these two objects, add them together again, this one will be negative now, this one will be positive, then it'll be the same as before the collision. And that's what we mean by conservation of momentum. So here's one way to express the equation of conservation of momentum. So the mass of the first object times its velocity plus the mass of the second object times its velocity, and again this velocity will be negative, will equal the mass of the first object times its velocity, which now this one is negative, plus the mass of the other object times its velocity, will equal each other before and after the collision. So this is before the collision, this is after the collision. So more formally, the law of conservation of momentum, it says that the total momentum of an isolated system of objects remains constant. That as long as you don't add any energy to the system, then momentum will be conserved for a system. So here's an example of this. So the total momentum in an isolated system remains constant. So here we have two railway cars, and one of them is moving with a certain velocity, and it collides with the second one that's initially at rest, and then afterward they're joined together, and then they move off with a new velocity having been joined together. So let's see how that's going to work out. So we'll call the masses of the two railway cars M1 and M2. And these are the usual sort of subscripts that we're going to be using. So I'll use the ones that you will commonly see. And so this one is moving with an initial velocity, so we'll call that V1 initial. Now it gets a little bit used to, the subscripts take a little bit of getting used to, but in time then you will get, it'll just become quite natural as to how you name things. And so just be aware of that as we're going along here. It may seem a little bit confusing at first, but it's not really. So then later, each car moves off with a velocity, and which is obviously going to be the same after the collision because they're stuck together now. So again, conservation of momentum would say that M1 V1 initial plus M2 V2 initial has to equal M1 V1 final plus M2 V2 final. So we can work with this equation here, and it actually simplifies quite a bit. So that when we look at this here, so we know that the velocities of these two cars are going to be the same because they're stuck together now, and so we can just call that V final. And so this simplifies down quite a bit actually. The algebra, this may seem a little bit complicated, but really it's not that once you start looking at these kinds of problems. So that's going to equal m1 plus m2 times the final velocity of the two cars together. And then this we can simplify even further actually, because we know that the initial velocity of the second one was 0, so that just disappears. So what we have then is just m1 v1 initial has to equal m1 plus m2 times v final. And in this case, if the two railway cars are the same mass, and we put in the initial velocity of this one, which is 24 meters per second, and we know that the two masses are the same, so we could just call them m, then this simplifies a little further yet, so that 24 times m equals 2m, because if these are both m, so m plus m is just 2m, then the final velocity will be 24 divided by 2, which is just 12.0 meters per second. And when you think about it, that kind of makes sense, because initially you have the momentum of the system is this mass times its velocity, and now it joins with the other car, so that the mass is now double, which means that the velocity will have to be half of what it was before. So the initial velocity of this one was 24 meters per second, and then afterward the two cars together, their velocity when they're joined now is 12 meters per second after their collision. So that kind of makes sense. All right, now some other examples of conservation of momentum that you may not have thought of before would be, this is another one here actually. A rocket blasting off is also a conservation of momentum, so that when they ignite the engines, then the gases that come out the engines, the exhaust of the engines, that's really just momentum causing the rocket to propel forward. So again, you have the same sort of thing happening. You have the hot gases, the exhaust coming out in one direction, and then you have the rocket going off in the other direction. Conservation of momentum is all that is really. Similarly, when a bullet is shot from a rifle, then when the rifle is shot, then you get the recoil action of the rifle, and anyone who shot a rifle has experienced sort of what they call the kickback of the rifle, and so that's the recoil. Because of the bullet going one way, then the rifle has, because of conservation of momentum, it has to move in the opposite direction, and so that's what causes the recoil. Any time that the bullet or cannon fire as well, if you've ever seen a cannon being fired, the cannon shot goes off in one direction, but the cannon itself is moved, or it starts in motion in the opposite direction actually. And when they fire them off ships, they have to make sure that the cannons are well secured to the ship. Otherwise, they will be going straight across to the other side of the ship. And so oftentimes they were secured with ropes, etc. But you see the same sort of a recoil in those sorts of examples as well. And so now, the last thing that we need to consider is when you have collisions, what happens to the energy? All right, so we've been talking so far only about momentum. Well, what about the energy? What happens to the energy? Because we're dealing with kinetic energy as well with the two objects that are in motion. In this case, we're not dealing with potential energy at all. We're only concerned with kinetic energy here. But you can actually have three different scenarios. And this is the first one, where we call it a perfectly elastic collision, where all the energy is conserved. So after the collision, you have the same amount of energy in the system as you had before. Now, generally speaking, that doesn't really happen. You always lose some energy, but in a way, I guess it is. Its energy still is conserved. It's just in a different form. We usually don't have the same amount of kinetic energy afterwards. Some energy is usually lost to heat. So in a way, energy really is conserved, but it's in a different form. So what you need to recognize is that as far as the kinetic energy itself is concerned, usually a perfectly elastic collision doesn't happen. What usually happens is you have some loss of energy in some way, and we call that an inelastic collision. So that's the second type. So you have elastic collisions, perfectly elastic, Then you have inelastic collisions, which are in between that one and the last one, which is perfectly inelastic, where the two masses stick together afterwards. And this would be an example of this. When they do ballistic testing, then quite often they fire a bullet into some kind of a mass that the bullet sort of sticks to, or the two masses move off together. And that would be an example of a completely inelastic collision. So you have a perfectly elastic collision where all the kinetic energy is conserved. Then you have the one in between, the inelastic collision, where there's some energy lost to heat. And then you have the perfectly inelastic collision where the two masses stick together and then move off together. Right? So those are the types of scenarios that you also need to know. So with conservation of momentum, make sure you think about the positive direction and negative direction, and then along with those types of collisions, we also analyze the energy before and afterwards.